Howdy Calculus 12.0. So today I am going to introduce two theorems, Rolle's theorem and mean value theorem. And I'm going to do it the way that I always like to do things. I don't want to just throw the theorem at you and leave you at that. I'm going to throw it at you, and then I'm going to backtrack and kind of give some justification as to why they are able to be used. And so this has to do with the behavior of functions that kind of involve derivatives and differentiability. And so it ties into the idea of graphing and kind of visualizing how these functions will behave. And so I'm going to start with Rolle's theorem. The reason why I'm going to start with Rolle's theorem is that Rolle's theorem is actually a corollary, or it is a basic building block of what we are going to then use to do mean value theorem, not main. So MVT and Rolle's, and here we go with Rolle's. So first of all, I'll read it to you, even though that's kind of a silly thing to do. Rolle's theorem states that if a function f is continuous on a closed interval from a to b, and differentiable on the open interval from a to b, and, so there's three conditions to this thing, f of a is equal to f of b, then, as a result, there is some number c in the open interval a to b such that the derivative of the original function at that c value is 0. Okay, that's a lot to digest all at once, especially if you're not used to reading things like this. So let's kind of go through this and get an idea of what it is that's being talked about. So I'm gonna draw on this as we come across each part. So f, so this little curve here in our particular example is our f function. And it has to be, in order for this to work out, between a, which is going to be our start position over here, and b, which is going to be our end position over here, what has to be true is that f, for this to be able to be applied, has to be continuous between a and b, including a and b, so it can't be discontinuous at a or discontinuous at b, but it also has to be differentiable on the open interval. So every piece in here has to have a derivative that gives you a numerical value. That does not have to be true at A or at B. So if this thing went completely vertical at A and B, which would give you something that's non-differentiable, as we saw earlier in the course, that would be okay. It could still satisfy Rolle's theorem. So as long as it's continuous, including the A and B, and differentiable, not including the A and B, and as a third condition, it also has to be true, and this is a very limiting condition. So this thing says that f of a and f of b have to be equal to each other. Otherwise stated, the height at the beginning of the interval and the height at the end of the interval have to be the same height. So it has to start and end at the same height. That height could be 0, but it could be 10. It could be whatever, any constant. But that height value at the beginning and the end has to be the same. So this is a really restrictive set of conditions. Obviously, Rolle's theorem isn't able to be applied in tons of different cases because unless you consider that you could take pieces of functions that you're interested in and probably find two places that have the same height and then apply Rolle's theorem in between those places, in between those endpoints. Okay, so those are all the conditions, and those conditions state that if this is true, these conditions are met, there is some number c. Now, in the example we have down here, there is a single c value. But there is at least some c, one c, could be more, in the open interval from a to b, so not including the endpoint, somewhere in the middle, where the derivative of the yellow function, the function that we're assessing to begin with, or looking at to begin with, that has a derivative of 0 somewhere in the middle. Now, I could probably describe this using what I might just say is common sense terminology, and have the easiest time explaining what Rolle's theorem actually means by doing that. What we could say is what goes up must come down. Now it makes sense from that point of view. And what goes down must come up. Now, what I mean by that is, if you have a function that goes up into the air and comes back down to the same level, and it's continuous and it's differentiable, so we have this nice smooth function that we can draw. No corners, no cusps, no discontinuities. So it is this nice smooth function. If that is true, then the only way to stop going up and start going down is to plateau and have a slope of 0. That's probably quite believable. Same thing, if you go down and then you find the place where this thing flattens out and starts coming back up, the slope there is going to be 0. If you were to kind of wiggle up and down a few times, then you would have multiple places where your slope would end up being 0. Oh, that's pretty bad freehanding it, but that's okay. So I'm going to do a little bit more formal of an explanation of that by using some theorems that we've already bumped into in calculus. So what we're going to start out with is by saying we're going to have 3 cases. So case 1 is going to be a really boring case. So I'm going to say that the f of x that we're interested in is actually equal to some constant. Now, I already have used A, B, and C as kind of things that are involved in this Rolle's theorem. So I'm going to say that the constant that it's equal to is m. Yeah, I'm going to use m just for the time being. This is a lot, maybe not. So slope, let's choose something else. I'm just going to go with d, I guess. So f of x is equal to d. Now, what that means is that for the entire function, because it's equal to d, if I were to take f of b minus f at a, and basically b minus a in the bottom, so delta y over delta x, my apologies for that, that's going to be equal to d minus d over b minus a, which is 0 over b minus a, which is 0. So what's going to happen is that the value of the slope from the beginning to the end is, of course, 0. But what I should have shown is that the instantaneous rate of change at any particular point is also 0. So I kind of bled into thinking I was doing mean value theorem for a second, which I'm not. So this part up here is not super helpful for what we wanted to show. All we really needed was the fact that if you have a constant value, then it's true that the slope is actually 0 everywhere, which means that in that case, it's obvious as to what's going on. If I say case 2, and we say f of x starts as an increasing function. Okay, so if f of x starts as an increasing function, and it ends up being that the increasing function that f of x is, that it starts at as, also has 2 endpoints that are at the same height, then because this thing is continuous, we can actually say that extreme value theorem from the last video can come into play. So extreme value theorem says that if you have a continuous function between a and b, then it would be true that there is some value where the function obtains a maximum value and the function obtains a minimum value. So f of x attains a maximum value somewhere. Let's say C, according to extreme value theorem, because it's continuous. So since that's true, what we can say then is that it has a maximum value. Now, because it's differentiable and it has a maximum value, Fermat's theorem states that it will be either differentiable and the maximum value that we know that it exists, that maximum value will have either a derivative of 0 or it will have a derivative that does not exist. But we said at the beginning of this that this is a differentiable function. So since it's a differentiable function, it does not have a derivative that doesn't exist somewhere in the middle. So Fermat's theorem would say that at that c value, we would have a slope of 0, which is exactly what Rolle's theorem says. So if we go up, extreme value theorem would say that there is a maximum that's obtained somewhere on that interval. In order for that maximum to exist, Fermat's theorem would say that there has to either be a slope of 0 or a slope that does not exist. But since the slope has to exist, the slope has to be 0, and therefore Rolle's theorem is safe if we start with an increasing function. Case 3, I'm basically not going to write anything down for, because that would be if you started with a decreasing function instead. And if you started with a decreasing function, everything's the same. So decreasing functions are guaranteed to have a minimum, any function is guaranteed to have a minimum on the closed interval. If you have a minimum somewhere on that closed interval, according to the extreme value theorem, then what has to be true is in order for that to be a minimum, Fermat's theorem says that the derivative has to either be 0 there or the derivative has to not exist. Since this is a differentiable function, the derivative has to exist, which means the derivative has to be 0 at that c value. So those are the only 3 cases. Your function either has to be absolutely horizontal, it has to be increasing to begin with, or it has to be decreasing to begin with. Those are the only 3 cases that you can possibly have, and in each of those cases you can show that there is at least one c value where the derivative is 0, so therefore Rolle's theorem has to be true for any continuous on the closed and differentiable on the open interval function. All right, so that's all I'm going to say about Rolle's theorem, and that's good enough for now. Now, what I'm going to do is actually just use Rolle's theorem real quick in order to show something that we started doing a long time ago, and we showed that this had at least one root. So we did that with intermediate value theorem. The way that we did that was we picked, I think it was 0 and 1. I'm going to try those. So if we call this f of x, and that's equal to x to the 3 plus x minus 1, and I just use a couple test values. So 0 would give you -1, and 1 would give you +1. So because of that, we can guarantee that there is at least one spot between 0 and 1 where you have a root. The way that we can guarantee that is because of the intermediate value theorem, which is really early on in the course. So intermediate value theorem says for a continuous function, if you start here and you end here, you have to go through here, something in the middle. Every value in the middle has to be cut through at least once. So in this case, we're basically saying at 0, you have a value of -1, and at 1, you have a value of +1. And so we're saying, because it's continuous, I dare you, connect those 2 points together without going through the axis. You can't do it, so it has at least one root. Now, it could squiggle up and down a whole bunch and have a lot of real roots, so let's show that that can't be true. What we're going to do is we need to find 2 values of this particular, that's right. So if we assume that there is a root at c, so f of c equals 0, and there's at least one. We know that this f of c exists because of intermediate value theorem. So let's say that there is another point somewhere along here where the value at that point is also 0. So what that would mean is we would have some other value, let's say at d, f at d is also equal to 0. We're going to assume that. Assume this is true. So according to Rolle's theorem, we have 2 points that are at the same height, C and D, or F at C and F at D would give you that 0 value. So if that's true, then F at D, let's try that again. So if we do have a D, then there must exist some E somewhere between C and D. So E must exist between C and D. So C and D are at the same height. So there must be an E somewhere in the middle where the slope is 0, because they're either connected with a straight line, which means the slope is always 0. It's an increasing function at first, so it would go up and then come back down. Slope is 0 somewhere here. It's a decreasing function at first, so it goes down, comes back up. Slope is 0 somewhere in the middle. So there is some E in between C and D where you would get a derivative of 0. What if that doesn't exist? What if there is no place where there's a derivative of 0? We can show that that's actually the case for this function. So this function is x cubed plus x minus 1. Its derivative is very straightforward. It is 3x squared plus 1. 3x squared plus 1, where is it equal to 0? Well, it's equal to 0 when x squared is equal to negative 1/3. Square root of a negative value, it doesn't exist. It's not a real number. So there is nowhere on the entire function where the slope is 0. And since it has one root and it can't have another root, because it basically, if it goes up, it doesn't come back down. If it goes down, it doesn't come back up. So according to Rolle's theorem doesn't work, but Rolle's theorem can't not work. So something about our assumptions are not true. This thing is continuous and it's differentiable. So what's the third condition? The third condition was that F at C and F at D have to be at the same height. So we assumed that F of D had to be at the same height as F of C, which was 0. That can't be true. There is no other point at the same height. So since there is no other point, it has exactly one root. So it has at least one root, but then you can show there isn't a second one, so it has to be exactly one root. That's a little Rolle's theorem extension on a question that we had done a long time ago. All right, mean value theorem. So mean value theorem is probably considered the only one that you really need to know, because mean value theorem also states Rolle's theorem inside of it. The problem is that if you want to come up with mean value theorem, you're probably using Rolle's theorem in order to show it. So it's kind of the Rolle's theorem can be used to help you show mean value theorem, but then once you have mean value theorem, it's questionable whether you need Rolle's theorem anymore at that point. So mean value theorem. If f is a function such that f is continuous on the closed interval, a to b, and f is differentiable on the open interval, a to b, then there exists a number c in a to b such that f prime of c is equal to f of b minus f of a over b minus a. Now, this is very similar to the last one. So f, this one's our f this time. Between a and b, this thing has to be continuous and differentiable. Same thing as last time. Continuous technically on the closed, differentiable on the open. Once you've kind of got that out of the way again, this says something a little bit different. This says there's no third condition anymore. This says that, sure, you have an f of a here, you have an f of b here. They're different. Great. So we have two different heights, and that's totally okay. What it says, which is really weird in a way, is that there is a slope somewhere in the middle where the slope of that point that's in the middle is the same as the average slope, or the slope of the secant that connects A to B. So if you just take A and B and you connect them with a straight line, it's going to have a certain slope. You cannot have a function that goes between A and B that is continuous and differentiable that does not have the same slope as the average slope. So if I, for instance, have A and B like this, and I just do something weird, so I go, so the average slope would be like this, And so the average slope would be like here, there would be 1, and somewhere around there, there'd be 1, and somewhere around there, there'd be 1. So there would actually be 3. What mean value theorem says is that it's going to always happen at least once. What you should do is pause the video, break out some paper, draw a bunch of continuous differentiable functions. So smooth, nice, loopy, curvy functions. Have to be functions too. Not allowed to do this failing vertical line test. So if you do that, you should experience that you cannot draw a function where you can at least visually see that there would be a possibility for the slope to be the same at one particular value as it is from the beginning endpoint to the final endpoint. All right, so deep breath. This is just another way of stating it. So you take the b minus a, multiply it up onto the other side, and you get f prime at c times b minus a is equal to f of b minus f at a. It says graphically what this means is that somewhere between a and b, the slope of the function is equal to the average slope between a and b. All right. Now, this one's the one that I'm going to be a little bit iffy. Hopefully I can do this. So I'm going to start out by saying we have y minus y1 is equal to the slope, which, so this I'm going to come up with an equation for the secant line. So this is my secant line specifically. So it's going to be y minus y1 is equal to the slope times x minus x1. If I were to fill in some of the information that we actually know what y1 is. That would be, I could take either point, but I'm going to take the one at a. So I'm going to say that this, if we say that the function is f of x, then we would have y minus f at a is equal to the slope value, but we know the slope because it's the slope of the secant line, which is just rise over run. So your rise is going to be f of b minus f at a over b minus a. And that's going to be multiplied by x minus x1, which is going to be just a. I guess I put a little extra bracket there that it wasn't needed, but that's okay. So I have then that this y function, or y, is just going to be equal to f of b minus f at a over b minus a x minus a plus f at a. All right, so I'm going to say that this y value that I have in this particular equation, I'm going to call it g, okay? So y is going, I'm just going to rename it as g of x, and the reason why is because I want to evaluate it at two different positions, and so it's easiest to do that way using function notation. So I'm just gonna, I'm just gonna rewrite the whole thing, even though it's gonna take me a little bit. Oh, come on, little one. There we go. B minus a, x minus a, plus f at a. All right, so I'm going to evaluate g at b and g at a. So g at b is equal to, anywhere where there is an x, I'm going to get a b. Now, that's not a very large amount of stuff there. So I would get f of b minus f at a over b minus a times b minus a, because we're doing g at b, plus f at a. Okay, so the b minus a that's here is going to cancel out with my b minus a that's there. And what I'm left with is actually f of b minus f of a plus f of a, which is the same thing as f of b. So g of b is equal to f of b. Okay? So that's fine. But I'm also going to say, let's evaluate this thing at g of a. So that would be f of b minus f at a over b minus a times a minus a plus f at a. So in this particular case, I'm going to get 0 times the original first thing, which gives me f at a, which gives me f at a. So I started to panic a little bit. It's fine. It's just I need another function, which is kind of crappy. But I had one of those moments where I was like, what am I doing? So what I'm going to do is I'm going to introduce h of x, and I'm going to say that it's equal to f of x minus g of x. Okay? So then h of a is equal to f of a minus g of a. But we just showed above that g of a, right here, is f of a, which is 0. H of b is equal to f of b minus g of b, but we showed up here that g of b is equal to f of b. So that's equal to f of b minus f of b, which is equal to 0. So h of x between a and b may be a Rolle's theorem function. And so let's check the conditions for Rolle's theorem. H has to be continuous between a and b, closed interval. So how is h defined? H is defined as the subtraction of two functions. As long as those two functions are continuous, then h will be continuous as well. What is f? Well, f is the beginning of this, which is basically it has to be continuous, it has to be differentiable. So it's guaranteed continuous, guaranteed differentiable. So what is g? G is actually just a line. It's the secant line. So this was our secant line, which we then called g. And so since it's a linear function, it is continuous and it is differentiable on that particular, it's continuous closed and is differentiable on the open. So both f and g are going to be continuous. So therefore h is continuous because it's the difference between the two. Both f and g are differentiable. Therefore h is also going to be differentiable. What that means is h is continuous on the closed interval, differentiable on the open interval, and as well, the third condition is that the height at b and the height at a have to be equal to each other, which is true. H of a and h of b, we've shown, are both actually 0, which means that h of x is actually a Rolle'sable function. So it is true that Rolle's theorem affects or can affect how we want to look at h. So what does Rolle's theorem say? Rolle's theorem says that there has to be an h of x where h of has to be a c. I don't know why I said h of x. Has to be a c between a and b where h of c, derivative of it, is equal to 0. So there has to be some c value in between a and b where h prime at c is equal to 0. So let's look at what h is. h of x is equal to f of x minus g of x. H prime of x then is equal to f prime at x minus g prime at x. H prime at c then is equal to f prime at c minus g prime at c, but it's also equal to 0. We know it's equal to 0 because of Rolle's theorem. So now the question is, do we know what h prime at c is and g prime at c? So we're going to go back up for a second, and we're going to look at what f is. So first of all, f is just our original function. So I'm going to say, I'm going to go back over here for a second. So f is our original function, so I'm just going to leave that as f prime at c. So 0, which is what h prime at c is equal to f prime at c minus g prime at c. Now, what is g? G is actually our secant line. So our secant line has a slope value of this. That is the value of our, and we could take the derivative if we wanted to. This would go away, and then so would, in this expression here, we'd multiply this by the x and this by the a. The part with the a in it would go away, and this whole thing would become the slope value, or the coefficient on x. So this right here is our slope of g. So it's f of b minus f of a over b minus a. So that is minus f of b minus f at a over b minus a. We're going to take that, put it over the other side of the equation, and say that f prime of c is equal to f of b minus f of a over b minus a. And that's exactly what mean value theorem states. So all that hoopla is basically to show that you can use Rolle's theorem in order to show that mean value theorem actually is true and is a thing. So we can therefore then use this idea of mean value theorem. Now it is very specific as well. It says that somewhere in between the endpoints, the slope instantaneously, the rate of change instantaneously, is equal to the average rate of change between your two endpoints. So I'm gonna leave it at that. And there are a few questions towards the end of the assignment that I'm going to put up tonight, and I'm going to put up this video tonight probably too. And those two things are the Rolle's theorem and the mean value theorem are going to appear in a couple questions, and what you'll have to know are the conditions for them and what they tell you once you have those conditions. So in the end, what you would like to know is that this basically box right here of information, conditions, if the conditions are met, statement. Same thing over here with Rolle's theorem. Oops. Conditions, if those conditions are met, statement. There's some number where the derivative is equal to 0. So that's good for now. It's a lot to take in. So again, don't necessarily need to replicate or duplicate. As you can see, I forgot about using the other function there. So I was like, oh, these two things aren't going to be 0, and then I had to define my h of x to be equal to f of x minus g of x. And if you do it that way, then you do get something that is rollsable, as I said before. And so you can finish that off. All right, I wish you all the best. I hope you're taking care, and hope I'm talking to you soon. Take care.